This video lesson is from the section called Rational Numbers as Exponents. We're still in radicals, we're still in roots, square roots, cube roots, things like that, but we're going to also talk about rational numbers as exponents. So let's review some things about radicals first of all. That if I ask you to simplify this problem, it says the square root of 3 squared, and I ask you to simplify this problem, the square of the square root of 3. Well, what's the difference between the two of these? In the first problem, well, you could look at that as the square root of 3 times 3, which is the square root of 9, which is 3. In the second one, you'd say, well, that's the square root of 3 times the square root of 3, but the square root of 3 times the square root of 3 is just, well, the square root of 3 times 3, which is what we had in the problem right above, which to the square root of 9, which is 3. And they're the same answer. So essentially from this, we could conclude that the square root of any number to a power is the same thing as if we took that root and put it to the power on the outside. You see this? The nth root of a to the m is equal to the the m power of the nth root of that number. So I already had this up here. So recall that 2 cubed and then squared afterwards is the same thing as 2 squared and then cubed, meaning it doesn't matter which order. When you have a power to a power, you're just going to multiply those exponents, and so either way, that's going to be 2 to the 6th. So this is just a little bit about radicals and how the order with the if there's a power in there doesn't make any difference, and the same thing with just exponent rules. Now, I want us to now take a little look into this idea here. That I want you to find some m such that if I take a to the m times a to the m, it's going to equal a to the first. I want you to think about that. In fact, if you want to, it'd be really good to actually pause the video and try to do this on your own. But let's look at it and see, when you unpause it, you'll see how I approach this. Well, a to the m times a to the m is just a to the 2m. And since I now have a to the 2m equals a to the first, bases are the same. So therefore, their exponents must be the same. So 2m must equal 1, and then solving for m, we would divide by 2, and we get that, well, m equals 1/2. If that's true, let's also look at the fact that we know that a to the first is the same thing as the square root of a times the square root of a. So therefore, the square root of a and a to the m must be the same thing. And over here we already solved for m, so let's put that back over here and say that, well, then the square root of a must equal a to the 1/2 power. And in fact, this is where the rule for rational exponents comes from. And we say that for any non-negative number a and any natural number index k, we've used that phrase before, but this time we are saying it as a to the 1/k power is the same thing as the kth root of that a. So how is all this used? Well, we might have a command that says write without rational exponents, meaning write in radical form. And here we have an example, 4 to the 5/2 power. We could write that as the square root, meaning that 1/2, that the denominator is 2, so we have an index of 2, the square root of 4 to the 5th, or we could write that as the 5th power of the square root of 4. In the first case, the one that's on the square root of 4 to the 5th, we end up with the square root of 1024. And over on the right, we get, well, we take the square root of 4 and we get 2, and then we raise that to the 5th power. And so, let's just see what happens here. Both of those are 32. If you'd have to me, I'd have to plug in the square root of 1024. I just don't have that memorized. But it is, when you plug in your calculator, you get 32. But 2 to the 5th power, I could do. I can do that on my fingers. And since they're the same, I look at the fact that the one on the right, this taking the square root of 4 first and then raising it to the 5th power, that seemed easier to me to do without the aid of a calculator. Now here's another problem. I have a to the 3rd, b to the 4th, all raised to the 1/5 power. And then we need to write that without rational exponents, meaning I need to write it with a radical symbol. Well, since I have the 1/5 power, I know that that's the 5th index. So it's the 5th root of a cubed b to the 4th. And here's another command. I could say write with rational exponents, not without, but this time I want it so there's no radical symbol. The radicand is 3a to the fourth, and that's very important to figure out what your radicand is, because you need to put your radicand with parentheses around it. And so we'll have a group of 3a to the fourth, all raised to the 1/7 power. Please make sure you use those parentheses. If you don't, you're not putting everything to the 1/7 power. Here's another one where we have the cube root of x to the 9th. So take that radicand x to the 9th, and we have that to the 1/3 power. Now we have x to the 9/3. You go, wait a minute, 9 over 3 reduces to the third, to 3. So we have x to the 3rd, and in fact, this is one of the ways we look at simplifying our radical equations, is put them into rational exponents, reduce the fraction, and you'll have a lower, you'll be able to reduce your radical equations. Now, we've been told in the past that we can only multiply when the indexes match, when we've been in radicals. So we've had a problem like this, the cube root of x times the 4th root of x, and we were told can't do it. But let's look at this for a minute, that when we write them in radical exponent form, rational exponent form, that becomes x to the 1/3 times x to the 1/4. And I look at those fractions, 1/3 and 1/4. Is there some way that I can make them where they have common denominators? And yes, I could write that as x to the 1/3 times 4/4 times x to the 1/4 times 3/3. And when I do that, I get x to the 4/12 times x to the 3/12. And we have that rule that when you are multiplying like bases, you add the exponents, and now we can add those two exponents because they have common denominators. So what we have to add is 4/12 plus 3/12, and we're going to get x to the 7/12. And so here's an example where we were just able to multiply two radicals that had different indexes. And the only way we could do that was to write them in rational exponent form. Now that x to the 7/12 could also be rewritten back in radical form, and I could say it's the 12th root of x to the 7th. Our last little topic is on negative exponents, which we have dealt with before. And the rule here is when you have a negative exponent, you're going to flip the base, and there's no real symbol for it. I usually like to draw a little loop-de-loop thing like that. That kind of helps me say that I'm going to flip the base. So we'll just look at a few examples of this. If I have this group, 6x squared, all raised to the -1. Remember, everything inside that parentheses is the base. And so I'm going to flip that. Instead of it being 6x squared over 1, I'm going to have 1 over 6x squared. Okay. In the next one, the entire base is 4p cubed. That's the base. The negative exponent says to flip it. So we're going to flip it, and it's still raised to the 2/5 power, but it's just not a negative 2/5 anymore. So I have it 1 over 4p to the 3rd raised to the 2/5. Now we could finish simplifying that. We could multiply the 2/5 times the 3. Well, we'd have to distribute to the 4 as well. So we would just leave it in this form, and that's all we would do with it. The next one, we have 1 over 5 to a negative exponent. When we flip 1 over 5, we get 5. So 1 over 5 to the -3/4 is 5 to the +3/4. And our last example here, I have 1 over x raised to the -1/3. That x would be flipped, but the whole thing is flipped again, and it becomes x to the positive. That's incorrect. It should say, hold on just a minute. There we go. It's x to the +1/3 instead of x to the -1/3, and that is the final answer for that. We will go over more of these examples in class and have a lot more practice in class with them as well.